For the first 5 questions, or the front of the quiz, we're going to be doing the gas laws equation you can find on the back of your reference tables. That's P1 V1 over T1 is equal to P2 V2 over T2. So for each of these, we're going to read the question, and what I tend to do is underline my different variables so that I know which one is which. So number 1, a sample of gas has a volume of 34 liters, so that's going to be my V1, and a temperature of 275 K, so that's my T1. Keep in mind that it has to be in Kelvin. If it's not, you have to convert it using the equation on the back of your reference tables, or recalling that all you have to do is add 273. And a pressure of 4.5 atmospheres, so that's P1. What will the volume of the gas be? So we're actually going to be looking for V2 at STP. STP, you can find it in Table A in your reference tables. For that, you will see that there are 2 temperatures and 2 pressures given. We want to use the temperature in Kelvin, so T2 is going to be 273. And our pressure we want to use in atmospheres because the one we were already given is in atmospheres. So that's 1 atmosphere. Now what I tend to do is I solve my equation for my variable first. So looking back up top at the equation I have written here, I'm going to be looking for V2. So in order to get rid of P2, since right now it's multiplied by V2, I would divide by P2. So my P2 divided, I'm just going to put it underneath and divided, and then that cancels out. And then to get rid of the T2, because right now it's divided by V2, I'm going to multiply. So my T2, T2. So now I have my equation already solved for V2. It's not the only way to do it. You could plug all your numbers in and then solve. I just find I don't rewrite letters wrong. I tend to rewrite numbers wrong. So now my T2 we said was 273K. P1 was 4.5 ATM. V1 was 34 liters. P2 we said was 1 atmosphere. And T1 is 275 Kelvin. So my kelvins cancel out, my atmospheres cancel out, my units are going to be in liters. So now because of the way I did this, I'm going to be able to do this all at once in my calculator. You're not going to be able to see my calculator, but I'll tell you what I'm doing. 273 times 4.5 times 34. Now I'm going to divide by the different things in my denominator. Technically I don't need to divide by 1, but I'm going to tell you I am. Divide by 1, then hit equals, and then divide by 275. Really important that you hit that equals. So my answer is going to be 100, and I'm going to look at my original volume. If you look here, it has 3 digits. This has 2. This has 3. This is actually a perfect 1, so infinite zeros after this, and this has 4. I'm going to give mine 3 digits, so 152 liters is my answer. Another sample of gas has a volume of 150 milliliters. That's my V1. At 173 Celsius. Now that's Celsius, so we have to convert it. I'm going to convert it right now. I'm going to add 273 to that number, and my T1 is going to be 446 Kelvin and 101.3 kilopascals. That's pressure. So pressure can, not P2, P1. Pressure can be in kilopascals or atmospheres. If the pressure remained constant, what that means is I don't need to include that in my equation. If the number is the same on both sides, they cancel each other out. So I'm not even going to include pressure. What would the volume of the gas be? So I'm looking for V2. at 546 Celsius. So I'm going to add 273 to 546, and that is 819 Kelvin. Typically, our equation is P1V1 over T1 is equal to P2V2 over T2, but I'm going to leave out my P's. So I have V1 over T1 is equal to V2 over T2. In order to get that V2 alone, I'm going to multiply by T2, so T2 ends up in the numerator. We're going to plug our numbers in. T2 is 819 Kelvin. V1 is 150.0 milliliters. T1, when we converted, was 446 Kelvin. So plugging into my calculator, 819 times 150, all divided by 446. My kelvins canceled out, so my answer is 275 milliliters. A sample of 200.5 liters, that's V1, of gas at STP, that's standard temperature and pressure. So let me look at the other numbers before I decide my units on pressure, but my T1 is going to be 273 Kelvin. At what temperature is the gas? So we're looking for T2. If the volume decreases to 150 liters, that's V2, and the pressure increases to 151.95 kilopascals. So the pressure that I'm going to use for my standard pressure in the beginning is going to be in the kilopascals units, which when you look at table A is 101.3 kilopascals. All right, so again, looking at our equation, we have P1 V1 over T1 is equal to P2 V2 over T2. What I find is students have a really hard time solving for something in the denominator. I would definitely solve first with this one because students tend to get this number in the denominator and express that as the answer when it's really the inverse of the answer. So to do this, I am going to, what I would do is just have these two switch places. You guys like to cross multiply, but really in the end, these two are going to switch places. And then to get rid of the T1, you would just multiply. Let me do it the way you would probably do it. P1 V1 T2 is equal to T1 P2 V2. And then to get T2 alone, you're going to divide by P1 V1. These cancel out. And hey, look, didn't P1 V1 end up switching places with T2? Here's T2 now in the numerator and P1 V1 over here. And then to get rid of this, I would just multiply, and look, it's multiplied on the other side. All right, let's plug in our numbers. So we have T1 at 273 Kelvin. P2 was 151.95, whoops, 5. See, I write numbers wrong, not letters. 5 kilopascals. And then V2 is 150.0 liters. In the denominator, we have P1, which we picked in kilopascals because the other unit we were given was kilopascals. And then V1, we started at 200.5 liters. Now to do this all at once in my calculator, 273 times 151.95 times 150 divided by 101.3 equals, and then divided by again the 200.5, and you're going to get our units that cancel are kilopascals and liters. So our answer is going to be in Kelvin, and the answer is 306 Kelvin. Pressure remains constant, so I can leave that out of my equation. On a sample of gas at 273 K, so that's T1, and a volume of 15 milliliters, so that's V1. What will the new volume, so we're looking for V2, of the gas be? What volume would the new gas be? This should be if the temperature increases to 360 K. So we're looking for V2, and we can leave P out of our equation altogether. So V1 over T1 is equal to V2 over T2. And to get V2 alone, we're just going to multiply by T2 on both sides. Oh, it's not letting me. Right over here, there we go. Now cancel those, and we can plug our numbers in. T2 is 360K. V1 is 15.0 milliliters. T1 we said was 275K. Our K's will cancel. 360 times 15 divided by 275, and you get 19.6 milliliters. All right, last question on the front. Which of the following samples will behave least like an ideal gas? Keep in mind that in ideal gas, the molecules need to be moving very quickly and very far apart. So an ideal gas would have a very high temperature and a very low pressure. Since they're saying least like an ideal gas, we're going to look for a low temperature and a high pressure. We're going to eliminate right off the bat B and C because those are high temperatures. And then when we look at our last two choices, we have 220 kilopascals or 103. So we're looking for the opposite. We're looking for high pressure. So the answer is A. All right, on the back side, they are 10 points apiece. Identify the following diagrams as either solid, liquid, or gas, which is the phase of matter, and then determine if the diagram is representing a homogeneous or a heterogeneous element, compound, or mixture. So we're saying three things about each of these. I kind of supported that a little bit by labeling what you should be answering for each one. So this first one, since our different particles are spread throughout the space of the drawing, it's a gas. Gases are always homogeneous. If you want, you can just circle that. And then this, we have, what we really have, these are each elements. But since there's two different ones going on there, this is a mixture. It's a mixture of elements, but it's a mixture. We have, for our phase, these are spread through just the lower part of this space. And if you notice, they aren't perfectly arranged. So I'm going to go with liquid. And then probably in order to answer the homogeneous or heterogeneous, it might be easier to answer this first because elements and compounds are always homogeneous. So we really only need to make that decision if it's a mixture. And what I'm seeing here is that there are two large open atoms associated with each of the dark ones. So I'm going to guess this is some molecule or compound where you have two of one element and two of the other. So I'm going to go ahead and say this is a compound, or if you want, you could circle that here. And compounds are always homogeneous. All right, now for these three, you have lots of choices on how to answer this. Just because your answer isn't the same one I picked doesn't mean it's wrong. The first one, we're drawing a homogeneous compound. For a compound, you have to have at least two different elements. And for a solid, it needs to be very organized. Now, I'm not very good at drawing, so this might not work out very well, but to do the simplest thing, I'm going to have my compound be just one open and one closed circle. And I'm just going to kind of take that pattern, and it should have its own shape, so I probably shouldn't have started right up against that, so I'm going to stop here so it's obvious it has its own shape. Open, closed. And there you go. And the box below, draw a gas, so I need to spread it out through the whole space. And they want a homogeneous mixture, which it would be as a gas, so I don't need to worry about that so much. But they're looking for two different compounds. So one compound might be this, which would be the simplest, but my other compound needs to look different. So I'm going to do an open and two closed to make it more obvious. All right, so as a gas, I'm going to spread this out open, two closed, two closed, and an open and a closed. Okay. Last one, we're looking for a liquid, so it's going to go across the bottom but be a little messy. It needs to be a heterogeneous mixture, which means that I want to really show there's different amounts or different mixtures within my liquid. The easiest way to do that would be to have two layers. And we need to have two different elements. Now, an element could be two of the same atom stuck to each other, or it could be singular atoms. I'm going to do one closed and one with two in it. Maybe my closed one is going to be my lower layer. Make it a little messy so it's not perfect. Okay, and then my second layer, I'm going to do my two. So now it's really obvious that they're not mixed evenly. And that's all there is for the quiz.